Today I'll be presenting my project titled A Comparative Study on Machine Learning Models in Financial Sentiment Analysis. The presentation is structured to provide a comprehensive overview of our research journey. We will start with an introduction to financial sentiment analysis, highlighting its significance in the financial sector. We will then discuss the specific objectives and the scope of our project, detailing what we aimed to achieve with this comparative analysis. Our methodology section is quite detailed. It includes pre-processing of data and exploratory data analysis to understand our datasets better, and code demonstrations to illustrate how we applied various machine learning models. Following the methodology, we will review the results and engage in a discussion about what these findings suggest. Finally, we'll wrap up with our conclusions and consider future directions for this line of research. Financial sentiment analysis, or FSA, has become essential in our digital era, where understanding investors' emotions can significantly impact financial market dynamics. By analysing textual data from news and social media, FSA helps us decode the market's moods, whether positive, neutral, or negative. This analysis is crucial, particularly in volatile markets, where investor sentiments can rapidly shift, influencing stock prices and investment decisions. FSA plays a role in larger integrated processes for forecasting future market trends. Our study integrates advanced machine learning techniques to enhance these forecasts. The diagram here shows an example of various market trend prediction processes. Our work, highlighted in red, specifically focuses on how different machine learning models interpret and predict based on these sentiments, thereby aiding in more accurate and timely market trend forecasts. The landscape of machine learning in FSA has transformed dramatically with advancements in technology. From basic statistical models to complex deep learning and transformer models, each has its role. Deep learning models have been pivotal in capturing deeper semantic nuances. Meanwhile, transformers have redefined benchmarks by handling extensive, unstructured datasets with their self-attention mechanisms, enhancing our understanding of investor sentiments across varied data sources. Our research is driven by the need to bridge gaps in current methodologies and enhance decision-making in financial markets. Despite significant advancements, there's a crucial need to evaluate these sophisticated models with their reliability and accuracy. By comparing models ranging from simple to advanced, like transformers, our study aims to identify the most effective tools for interpreting financial sentiments. This endeavour not only advances our technical knowledge, but also aims to set a benchmark in FSA that marries technical rigour and practical relevance. This study intentionally excludes numerical, behavioural, or other data types to pinpoint the impact of textual data alone. In terms of data handling, our approach revolves around leveraging existing datasets. We put a strong emphasis on pre-processing stages and feature engineering specific to financial sentiment analysis to enhance the model's input quality and relevance. We do not aim to test real-world adaptability or direct market application in this research. Instead, our core objective is to rigorously analyse and compare the performance of various models from simpler statistical models to more complex deep learning and transformer architectures. This comparison is grounded in robust performance metrics tailored to highlight each model's efficiency and limitations specific in our scope. Finally, we will wrap up our study with strategic recommendations and directions for future research based on our findings regarding model accuracy and performance. We meticulously gathered datasets from various sources. First, we include over 22,000 tweets from financial influencers indexed as dataset 1. Next, indexed as dataset 2, the financial phrase bank includes around 4,800 sentences from news articles about Finnish stock market companies. Dataset 3 is our adapted version of the FIQA dataset, originally designed for a financial opinion mining challenge. Here, we have categorized sentiment scores into our analysis framework. Furthermore, we incorporated datasets from an AI analytics company with dataset 4 comprising of 500 social media discussions on stocks and dataset 5 including 562 Reddit comments on cryptocurrencies. Each dataset, clearly indexed, has been carefully selected and adapted to ensure a comprehensive view of financial sentiments. These indices will guide our discussions of methodologies and results later in this presentation, forming the empirical foundation for our analysis of different machine learning models. Next, we'll discuss our approach to enhance dataset quality through key pre-processing steps, including formatting, formation, and cleaning. We begin with data formatting, where we ensure all datasets comprising of text, sentiment, and URL fields are uniformly formatted. This step guarantees that our data is consistent and compatible across different analysis, simplifying both processing and training. Next, data formation involves creating specific datasets tailored to each model's needs. For simpler models, our dataset includes basic features. For more complex models, we add more detailed information like URLs and company names. This approach not only maximizes the performance of each model, but also elevates the quality of our data. To further enhance data quality, we remove duplicates early in the process. This ensures that any similarity in our data is due to actual textual characteristics, avoiding bias in our analysis. Our text cleaning process involves removing non-essential elements like usernames and URLs, tokenizing text, eliminating stop words, and applying stemming. These steps focus the analysis on relevant text and reduce complexity, preparing our data for effective model training. Let's look at our cleaning process in practice. Our initial cleaning process removes the URL and the $ in the ticker symbol, as well as converting all text into lowercase. In the final cleaning phase, we refine our text further by removing common stop words like up, to, and in, and finally applying stemming. Our final pre-processing steps involve handling missing values and converting text into numerical formats like TF-IDF and bag of words for traditional models. For the transformer models, we leverage their capacity to understand context without these transformations. In conclusion, through careful data preparation, we ensure our models are well equipped to perform accurate sentiment analysis. This flowchart illustrates the algorithm we form, covering data formatting and formation, our detailed cleaning process, finally handling missing values and text vectorization, culminating in 6 pre-processed datasets. Next, we'll be exploring the initial phase of our machine learning study, the exploratory data analysis, or EDA. This phase is crucial as it helps us begin to understand the data we're working with and guides our subsequent modeling strategies. Let's start by examining the sentiment distribution across our datasets. As you can see, there's a significant imbalance with a predominance on neutral sentiments. Recognizing this early allows us to implement corrective measures during model training to avoid bias and improve predictive accuracy. Finally, we conduct a bias analysis to ensure our models are fair and robust. Our examination of various sources revealed how sentiment can vary significantly, influencing the reliability of our predictions. In conclusion, our EDA has provided invaluable insights that shape our approach to building effective machine learning models for financial sentiment analysis. Our next steps will involve applying these insights to model development and training. Now let's describe and contextualize the various types of machine learning models we've used in this study. First, we have traditional models. Logistic regression is a fundamental statistical approach that models the probability of a default category. It's straightforward and effective, particularly when we have a linear relationship in our sentiment data. Next, decision trees. These models use a tree-like graph of decisions and their possible consequences. It's a visual and intuitive method allowing easy interpretation of how decisions are made. Next, we delve into ensemble models, which combine predictions from multiple models to improve accuracy. Random forest uses a multitude of decision trees. It's known for high accuracy and the ability to run in parallel, making it robust against overfitting, an attribute when an algorithm fits too closely to its training data and performs worse on new data. XGBoost, which stands for Extreme Gradient Boosting, is renowned for its performance and speed, often winning many machine learning competitions by handling large volumes of data efficiently. Moving to more complex deep learning models, we have CNNs, which were originally designed for image processing. We can also apply them to sequential data like text for pattern recognition and classification. Another deep learning application are LSTMs, or long short-term memory. This is a type of neural network that is excellent at learning order dependence in sequence prediction problems, which is essential for understanding the flow of sentiments in sentences. Lastly, we look at transformer models, which have recently revolutionized natural language processing. BERT is a model that learns contextual relations between words in a text. Next, we have FinBERT, a fine-tuned version of BERT, specifically pre-trained on financial text to capture the unique vocabulary and sentiments of the financial domain. Lastly, GPT, or Generative Pre-trained Transformer, is a state-of-the-art language model that uses deep learning to produce human-like text, enabling nuanced understanding and generation of financial sentiments. Before we look at our code for model implementation, it's important to look at the metrics and techniques that will appear in subsequent demonstrations. First, accuracy. It gives us a basic measure of correct predictions, but it's not always reliable in imbalanced datasets like ours. Therefore, we complement it with F1 score, which balances precision and recall, ensuring our model accurately captures all relevant sentiments. We also use a confusion matrix to understand the types of errors our models make, which is crucial in financial contexts where errors can have substantial implications. Furthermore, we analyze our models with ROC curves, assessing their ability to distinguish between sentiment classes effectively. This helps in fine-tuning the sensitivity and specificity of our models. For model validation, we employ k-fold cross-validation, using both standard and repeated methods to ensure thorough evaluation. We also refine our models through hyperparameter tuning, utilizing both grid and randomized search methods to find optimal settings efficiently. Logistic regression is a powerful statistical model used to estimate probabilities, which makes it particularly suitable for categorizing sentiments. Our methodology incorporates bag of words and TF-IDF for feature representation, and robustness is ensured through repeated k-fold cross-validation. We assess performance using ROC curves and confusion matrices. To handle our dataset's inherent class imbalance, we adjust the class weight parameter and test various solvers like liblinear and Saga for optimal efficiency. A classification report quantifies our findings, showcasing precision, recall, and F1 scores. Moving from traditional models like logistic regression, we present an example of ensemble learning, specifically bagging with random forests. Bagging involves multiple decision trees, which are simple models that make decisions based on data features. These trees are trained on varied data subsets and combines their predictions to stabilize and improve accuracy. We experimented with different random forest configurations to leverage the collective strength of these trees, such as feature bagging and voting ensembles. We measured model performance using the out-of-bag score, which estimates accuracy with data not used in training. We also run hyperparameter tuning to fine-tune our models for better performance. Finally, we validate our model's effectiveness using rigorous repeated k-fold cross-validation. Building on the strengths of ensemble methods, convolutional neural networks, or CNNs, provide a deep learning-based framework for analyzing text. As demonstrated in recent studies, CNNs are top performers among deep learning applications in this field. In our approach, we start by pre-processing the data, transforming sentiment labels into numerical formats, and using an embedding over frequency technique to improve text segmentation. We then employ a CNN architecture designed to capture and learn from our financial textual nuances through layers that reduce complexity and enhance interpretability. The model undergoes rigorous training and evaluation, including k-fold cross-validation, ensuring its robustness and accuracy in sentiment classification. This process not only enhances model performance, but also provides a clear insight into its predictive capabilities. We conclude our model exploration discussing transformer-based architectures, particularly BERT, which stands for bidirectional encoder representations from transformers. Unlike traditional models that process text linearly, BERT reads text both ways, enhancing its understanding of context and word relationships. Before training, we must also prepare the data with a tokenizer suitable for BERT. Now we can fine-tune the model. Fine-tuning involves adjusting a pre-trained model which is already knowledgeable in general language to specialize in a specific task. Similarly to all of our previous models, we assessed BERT using a confusion matrix and a classification report. We find that Bag of Words showed superior performance in accuracy and F1 scores, particularly in logistic regression on dataset 1. This suggests that Bag of Words is more effective in capturing essential textual features for financial sentiment analysis tasks, highlighting its robustness over TF-IDF in complex datasets. Advanced models such as Random Forest, XGBoost, CNN, and LSTMs demonstrated superior performance, particularly CNNs and LSTMs, which achieved nearly 97% accuracy on dataset 1. This highlights the advantage of using deep learning architectures that can intricately model the non-linear and sequential dynamics present in text data, leading to significant improvements in predictive accuracy. Accurate classification of negative sentiments remain a challenge across all models, indicating a potential focus for further algorithmic refinement. Large language models like FinBERT and GPT-3.5 did not match the high performance of CNNs and LSTMs. These were the only two models that weren't trained on our data initially. This suggests that domain-specific adaptations are crucial when employing general LLMs for specialized tasks such as financial sentiment analysis, despite their advanced capabilities. Our study rigorously evaluated various machine learning models from logistic regression to advanced CNNs and large language models, using data from news articles and social media. We achieved optimal performance through detailed hyperparameter tuning, with CNNs excelling at a 97% accuracy rate. A notable challenge was the underrepresentation of negative sentiments in datasets, affecting our accuracy and highlighting an area for model improvement. Looking ahead, enhancing model generalisability and sensitivity to negative sentiments is crucial. Strategies like data augmentation can help balance sentiment representation and boost performance. Moreover, extending our research to include computational assessments like latency and memory usage will provide insights into practical deployment of these models in real-world financial systems. Evaluating the models against live data will also be pivotal in bridging the gap between theoretical research and practical application. This study not only met its objectives of rigorously comparing machine learning models for financial sentiment analysis, but also laid out a robust groundwork for future advancements in financial technology. Thank you for watching this presentation. I appreciate your interest and invite you to explore further details in our full report. Please feel free to reach out with any questions or discussions. On this slide, I have included references for all images used.